I'm going to talk about understanding statistics. And this whole story begins with how we learn mathematics. When we learn mathematics, we were used to thinking of fixed numbers. So you have a number line and your teachers or your parents says, how many dogs are there? And you identify on the number line, there are 2 dogs. And then you get another dog. And you say, well, how many dogs are there? And you identify on the number line that there are 3 dogs. And doing math like this gives us this sense that numbers are fixed, which they are, but it's what we call a deterministic way of thinking. Math is deterministic. You've got something that's 2 or 3 or 4 or 2.5. The numbers are what they are. But the world tends not to be deterministic, but stochastic. That is, the numbers kind of, you could think of them as vibrating. And so in the deterministic world, we say something like 4 is bigger than 3. And 4 is always bigger than 3. If you can find an instance in which 4 is not bigger than 3, you have upset everything we think we understand about mathematics. That's a deterministic way of thinking about numbers. But in statistics, numbers are stochastic. So it's like saying not 4 is bigger than 3, but dogs are bigger than cats. Generally speaking, that's correct. Now, you can find a particular cat that's bigger than a particular dog, but it doesn't, that particular example doesn't negate the truth of the statement that in general, dogs are bigger than cats. That's a stochastic statement. And so when we study science in school, we study what we think of as the hard sciences, and we think of them as hard sciences because the measurements in these sciences, think physics and chemistry and biology, the measurements that we undertake are deterministic. So you say things like increasing the number of protons alters the chemical element, or the greater the distance, the less is the gravitational attraction, or applying force to an object will cause the object to accelerate. These things happen every single time. They're deterministic. But in the soft sciences, the social science, amongst them is economics, the truths aren't deterministic, they're stochastic. And so you say spending more time studying will get you a better grade. Generally speaking, that's correct. It's not correct in every single instance, but in general, it's correct. When the minimum wage rises, unemployment rises. In general, that's correct. It's not true in every single instance, but in general, it's correct. Regular exercise will make you live longer. In general, that's correct. These are stochastic statements, statements that are true on average, even if they aren't true in every particular instance. And so stochastic phenomenon, because they vibrate like this, they're difficult to describe. So I ask you a question: what's the typical number of children in a household? And so we take a survey of households, we get these 13 households, and we ask how many children in each household. And you could say, well, the answer to the question, what's the typical number of children? Well, the average is 2.6. We call that a mean. The average is 2.6. Well, that's not very useful. It doesn't make sense because you can't have 0.6 of a kid. What does it mean to have 2.6 children? And so we have another measure, and that measure we call the median. That's the guy in the middle. And if you line up all the households from the least children to the most children, the guy in the middle is 2. He has 2 children. But you look at this sample and you say, well, that doesn't make sense either, because you're asking what's the typical number of children, and 2 is the least common of all the numbers of children here in my sample. So there's another measure we can use. It's called the mode. And the mode is the most frequent observation. And if you look at these households, the most frequent observation is a household with no children. And so you say, well, the mode is 0. Well, if you're trying to get your head around the typical number of children in a household, that doesn't make sense either, because most of these households have children. And what we're bumping up against here is the problem of taking this very rich, complex thing, a stochastic phenomena, children in a household, and we're trying to reduce it to a deterministic number, 2.6 or 2 or 0, and none of these numbers fully captures the essence of what's going on here. So this is one of the problems we have with stochastic processes. It's difficult to talk about them. And because it's difficult to talk about them, we arrive at certain misconceptions, and I'll talk about some of them. For example, a percentage change and a percentage point change are different things. There was an instance back in the early 2010s where Michigan politicians were proposing to raise the state sales tax from 6 to 7%. And the politicians said in defense, look, this isn't a big deal. It's a 1% increase from 6 to 7%. Yeah, except that's not a 1% increase. That's a 1 percentage point increase from 6 to 7. It's actually a 17% increase. That is, if I have a 6% sales tax and you figure out how much taxes you owe, and then we raise that tax rate to 7%, and you figure out how much taxes you owe, the taxes you owe just went up by 17%. 17% versus 1 percentage point. Another misconception that we have, a declining share doesn't necessarily mean less. So this is something that people talk about a lot when we talk about poverty in the United States. They say, look, in 1969, the poorest 20% of Americans earned 4.1% of all the income. And in 2019, the poorest 20% of Americans earned 3.1% of income. And people will compare those two numbers and say, look, the poor are worse off in the United States today. They only get 3.1% of income when before they used to get 4.1% of income. Except, here's the thing, from 1969 to 2019, total income rose by 20%. So although the share of income that the poorest 20% earn today has declined, it's a smaller slice of a much bigger pie. And so the amount of income that the poor earn today is actually, even adjusted for inflation, is actually significantly larger than it was in 1969. Yes, it's a smaller slice of the pie, but it's a smaller slice of a much larger pie. Another misconception, things that sound similar in English may be very different in statistics. In the early 2000s, there was a class action lawsuit filed in New York City against the New York City Police Department. And the class action lawsuit said that the New York City Police Department was promoting males to the male police officers, promoting them to detective at a greater rate than they were promoting the females. And so they said, look, this is evidence of gender discrimination. So the prosecution in this case asked the question, what are the chances of an officer being a promoted female versus what are the chances of an officer being a promoted male? That's the question they asked. It turns out that that's the wrong question. The right question sounds very similar. The right question is, what are the chances of a female officer being promoted? So the two questions, the wrong one, what are the chances of an officer being a promoted female? And the right one, what are the chances of a female officer being promoted? In English, they sound almost the same, but here's the difference in statistics. When I ask, what are the chances of an officer being a promoted female? We look at all the officers and we ask the question, how many of these have been promoted? And then we take the promoted females and we divide it by the total number of officers, and you get 25%. And the prosecution pointed to this number and said, look, this is evidence of gender discrimination. We're getting females being promoted at a rate of 25% when it should be 50%. But here's the thing, they asked the wrong question. The right question to ask is, what are the chances of a female officer being promoted? To ask that question, you first look at all of your female officers and you ask how many of these officers were promoted. You then divide the number of promoted female officers by the number of, you divide the number of promoted female officers by the total number of female officers. And that number is 67%. The two questions sound almost the same in English, but they're very different. In fact, the outcome of this gender discrimination case hinged on translating that question into statistics correctly. So this second question was the correct question, and in fact, the case was dismissed because once they conceptualized the question correctly, they realized that there was no gender discrimination here, at least according to these numbers. Another misconception: what's true, and this is probably my favorite of all of them, what's true for the whole is not necessarily true for the parts. And let me show you something even interesting. Very interesting. Here it is. So you got a sociology department, and we're looking to hire people. We have 5 male applicants who have applied for a position in the sociology department, and the sociology department hires one of them. So the probability of a male applicant being hired in the sociology department is 1 out of 5, 20%. Also, 8 females apply for positions in the sociology department, and the sociology department hires 2 of them. So the probability of a female applicant being hired is 25%. So in the sociology department, if you're a female applicant, you're more apt to be hired than if you are a male applicant. How about the math department? Math department, similar thing. 8 males apply, the math department hires 6 of them. So if you're a male, there's a 75% chance you got hired. How about the females? Well, there were 5 applicants, and the math department hired 4 of them. If you were female, the probability of you being hired was 80%. So in both cases, the sociology department is erring on the side of hiring women, the math department is erring on the side of hiring women. But if you put the two together, the total number of male applicants here is 13. The total number hired is 7. 54% of the male applicants were hired. And if you do the same thing with the females, you see 46% of the females were hired. And here's the fascinating thing. I'm going to tell you 2 things that sound contradictory, and they're both correct. The sociology department is, if you're a female, you're more likely to get hired in the sociology department than a male. If you're a female, you're more likely to get hired in the math department than a male. But if you're a female, you're less likely to get hired in the combination of the two than if you're a male. This is a phenomenon that we call aggregation bias, and it shows up lots of places. What's true of the whole is not necessarily true of the parts. So I give you this simple example. Here we have a group of people, and this is in 2010. Person 1 is 90 years old. Person 2 is 80 years old. Person 3 is 70 years old. It goes down the list, and person 10 was just born. Person 11, person 12 haven't been born yet. Person 10 was just born today. He's 0. This is 2010. The average age of my people here, 45 years old. Now, go away and come back 10 years later. 10 years later, what do you see? Someone new has been born. Person 11 was just born yesterday. He's 0. Person 10, he had been born 10 years ago. So today he's 10 years old. Person 9 was 10 a decade ago. Now he's 20. All of these people have aged. Oh, and person number 1, he died. So he's no longer there. Now look at the ages here of my people in 2020. The average age is 45. Go away, come back 10 years later. It's now 2030. And yesterday, person 12 was born. He's 0. Person 11, who had been born the last time we were here, he's now aged. He's 10 years old. Person 10 was 10 years old. He's now 20 years old. Everybody's aged. Oh, and person 2 has died. What's the average age of everybody? The average age is 45. Now, here's the aggregation bias. 2 things, both of them are true. The average age in 2010 was 45. The average age in 2020 was 45. The average age in 2030 was 45. The average age was constant. It's always the same. It's 45. And yet, every single person aged. It's an aggregation bias. What's true for the whole, the average age stayed the same, is not true of the individuals. Each individual got older. Now, that's a made up example, but we do this all the time with real numbers. You'll hear politicians talk about how horrible it is that the median worker's wage has stagnated since the 1980s. And here you see, this is the actual data. This is the median workers of the guy in the middle, the median American worker's age, wage and salary adjusted for inflation. And you could say it goes up a little bit, but basically it's kind of flat. And we're talking whatever this is, 30, 40 years here. And so politicians point to that and say, see, this is what's wrong with our economy. Nobody can get ahead. The median worker's wage is the same today as it was 30, 40 years ago. But it's an aggregation bias. Because what happens with wages is the same thing that happened with the ages that I just showed you. As time goes by, people get raises, they start earning more. Older people who are at the top of their earning career, when they hit retirement, they go away. They're not earning anymore. It's like the people who died. And new people come into the job market, freshly minted graduates, and they earn a low amount because they're just entering the job market. That's like the people who are being born. And so when it comes to workers' wages in this country, we follow the same pattern that I showed you with those people's ages in those charts. In fact, if you track the median worker over time, you find that the median worker looks like this. What this blue line you're seeing is the typical American's wage as he goes through his working career. He starts off adjusted for inflation, low at $25,000, and he goes through time. He ends up earning up to $50,000 by the time he goes to retire. Each worker's income is actually doubling over the course of his career, despite the fact that the average has remained the same. It's an aggregation bias. Observation bias is a similar thing, and I won't ask you to answer, but take a moment and think about it. What fraction of US workers do you think earns the minimum wage? What fraction of US workers do you think earns the minimum wage? 50%, 30, 20, 10, down to 0, down to 1. And the answer is, of all of these, E comes closest, 1%. And here you're looking at the fraction of US workers earning the minimum wage, and look at that vertical axis. These are all, the top of the chart is 1%. Everything below that are fractions of 1%. When we think about the minimum wage, we have this tendency. In fact, I ask my students, how many people do you think earn the minimum wage? And they typically say around 30%. That's way off. It's around 1% or less than 1%. And why? What's going on here? What's going on is an observation bias. Think about it. When you go out into the world to buy things, you go to Walmart or you go to the grocery store or you go to Starbucks or McDonald's, who are you interacting with more often than not? More often than not, you're interacting with somebody who's earning the minimum wage. And so you have an observation bias. When you go out in the world and you transact, you buy and sell, or you don't sell things, you buy things, you're interacting with minimum wage workers predominantly. And so you get this sense that many of the workers are minimum wage, when in fact they aren't. You just aren't seeing the ones who aren't minimum wage. With statistics, we go and collect information, we run tests, and we present evidence. And one of the things that happens often is that non-statisticians confuse evidence and the absence of evidence. Evidence tells us something. The absence of evidence doesn't. I'll give you an example. Here you are sitting in your house and you ask yourself, is the dog inside? And you collect information, you look and you see there's a dog. You have evidence. And so you conclude the dog is inside. Now let's do it again, but this time the dog's upstairs. And you ask yourself, is the dog inside? And you start to collect evidence. You look and you don't see the dog. You look around, you're not seeing the dog anywhere. There's no evidence that the dog is inside. Does that mean the dog is outside? No. The dog could be upstairs, it could be in the kitchen, it could be outside. But notice what's happening here. The absence of evidence that the dog is inside is not the same as evidence that the dog is outside. Let me say that again. The absence of evidence that the dog is inside is not the same as evidence that the dog is outside. The absence of evidence is simply no conclusion. I can't say anything. I have no evidence. Now, this seems kind of simplistic, but we make this mistake all the time. There was a study published in the 1990s about the minimum wage. It's a famous study by two economists, Card and Kruger. Card just recently won the Nobel Prize. And in this study, they did not find evidence that raising the minimum wage caused unemployment. They did not find evidence that raising the minimum wage caused unemployment. The media grabbed this and pronounced that raising the minimum wage doesn't cause unemployment. And notice the media made the same mistake that I just warned you about. Absence of evidence is not evidence of absence. Card and Kruger found nothing. They got no result, which is very different from saying they got a result that the minimum wage doesn't create unemployment. Definitions matter. When we talk about wages, and frequently people will say things, there are some politicians I can think of who say often that median wages haven't grown over time. And this is the picture that I showed you a little bit earlier. But here's the thing, definitions matter. Workers aren't paid wages. They're paid compensation. Compensation is a combination of wages and employer-paid benefits. And if you look at the correct definition, compensation, you see this, that adjusted for inflation, worker compensation is actually up 45% since 1970. So the definition, what is it you're talking about, matters. The context also matters. As of June of 2021, 550,000 Americans had died of COVID. And this is the number that the media points out, and everybody says this is horrible, we need to do something. And I'm not saying it isn't horrible, but I am saying that context matters. Because although 550,000 Americans on an annualized basis are dying of COVID, the number who die of heart disease and cancer together are about twice that amount. And what's different about the heart disease and the cancer is while COVID, even left untreated, we would eventually get a herd immunity. You don't get herd immunity to heart disease and cancer. So COVID comes along and it plays out for as long as it plays out, and then it goes away. Heart disease and cancer, they don't. Year after year after year, you keep on getting these deaths. And why does the context matter here? The context matters because if we're going to do something and say, look, we need to shut down the economy, we need to shut down schools or whatever it is because of the danger of this thing, it's important to ask, are we treating other things that are even more dangerous with the same care? For example, if you look at COVID deaths by age, look at the left of this graph, you see the people who are aged 0 to 17, people who are aged 18 to 29. That's the number of deaths that have occurred from COVID amongst those age groups. That number is 1/5 of the number in those age groups that die of suicide annually. So again, the context, if we're going to go to the extremes that we have gone to protect young people from COVID, why aren't we going to 5 times that number of extremes to protect them from suicide? And the reason that we aren't doing that is because we've lost sight of the context. We look at this thing and we say this is a very bad thing, and indeed it is. I don't mean to say it isn't. But there are other things that are far, far worse that we have treated less carefully. Finally, last thing, when you think about statistics, don't follow your heart. In 2001, in an apparent suicide, a teenage pilot flew a private airplane into a building in Florida. This was right after 9/11. The teenager, it turns out, was one of 37 teenagers across the United States who were using Accutane, which is a prescription drug for severe acne. 37 teenagers using Accutane committed suicide that year. And there was a huge outcry. Concerned parents were calling for the FDA to ban Accutane. This was the heart. You see this, oh my God, 37 kids using Accutane have committed suicide. We need to do something. And the FDA, under political pressure, came close to banning Accutane. But here's the problem. We're thinking with our hearts, not our brains. If you think with your brain, you don't just look at how many Accutane users commit suicide. You also look at how many people who don't use Accutane commit suicide. And you look at how many people who take Accutane don't commit suicide and how many people who don't take Accutane don't commit suicide. You look at all of this. And if you look at all of it, you come to a conclusion that the incidence of suicide amongst teenagers not taking Accutane was 8 times that amongst teenagers who were taking Accutane. And that actually makes sense because it's hard enough being a teenager, let alone being a teenager with severe acne, and the Accutane helps to treat that. It helps takes one more pressure off of what's already a hard thing of being a teenager. The hard thing here, the hard lesson is, when this event first happened, we tried to think with our hearts, and we saw 37 teenagers who committed suicide using Accutane, and we said, oh my God, we've got to ban this. We came close to banning something that actually prevented teenage suicide. We would have actually made the matter worse had we not taken a deep breath and thought about this with our brains instead of our hearts. So if you've enjoyed this, Ms. Cromer was kind enough to mention my podcast, Words and Numbers. I have a podcast. We come out on all the podcast players every Wednesday. And particularly if you're interested in government and economics from the perspective of a regular person who's just interested in the world around them, check us out.